Okay, so we are still looking at indeterminate axial. This again is just a temperature problem. It doesn't have an applied force, but we have a developed force because of the expansion. So we have two cylindrical rod segments that are fixed to the rigid walls such that there is a gap of 0.01 inches between them when T1 equals 60 degrees. Each rod has a diameter, so we weren't given area, but it's a diameter. We can check the units and see it's not area. Determine the average normal stress in each rod if T2 is 400. Also calculate the new length of the aluminum segment. Okay, so as always, we start with equilibrium. And as we heat these up, okay, right now, if I summed forces in the x direction, I don't really have anything there, although it's holding weight on, and we never ever consider the fact that we have self-weight, but consider there's actually self-weight, so there's already something going on at the wall, but we don't have any stress within the system because we're not applying any loads. So they're sitting there. As I heat this up, they're both going to want to expand. And as they expand, they're going to want to like push. I don't know if you my fingers are pushing on each other. And as they're pushing on each other, they're going to be pushing back on the wall, which means the wall has to be pushing back on them. So let's draw our equilibrium equation. See what we have looking at here. They're the same diameter, so I'm just going to draw it like that. So I have heated it up and they are both expanding. And as they are expanding, they are wanting to, get longer. And so these wall forces are having to push them back in so that they're not punching through that wall. And one of the things I want to notice is that I could say FA, FB. It doesn't matter. Let's just call it FA and FB. We don't have labels on there. And then let's sum the forces in the x direction. They equal 0. So I have FA minus FB equals 0. So I can say that FA equals FB, and we're just going to call that F. It's the same. And again, if I want to find those internal stresses, if I'm pushing with an F, and I have this member here that's the copper, then it has to have an internal equal and opposite. So that internal force of the copper has to equal F. And I can also see that this is in compression. So it's a negative force, negative stress, negative delta. If I look over here and I want to find the internal force here of the aluminum, and I have this external force F. If I sum forces in the direction, I'll find it's equal and opposite. So my force in the aluminum also just equals F. And I want to note also this is in compression. So it's a negative stress, negative deformation. So now we have to go back and consider what's happening with our deformation. So I think I'm going to come over here this time. So deformation. So let's pretend like there wasn't a gap there. So this is kind of like a problem we've already done. If I were to heat this up and it wants to expand, okay, at the end of the day, there can be no overall change in length, no overall change in length. So I know that the change of the copper plus the change in the aluminum has to equal 0, okay, has to equal 0. But there's actually a gap in place, and the gap is 0.01 inches. So they can slightly move. They can actually move 0.01 inches. There is a little wiggle room. So if we don't heat it up enough, it won't even close the gap, and then we don't have an issue. So we actually do have some wiggle room. So they will be able to expand and close in that gap. So this is what it looks like when you close a gap. Now, what goes into my all of this? What goes into my copper and what goes into my aluminum deformation? Well, this is going to come from both that internal force that's created by compression in the wall plus temperature change. Again, internal force plus temperature change. So let's get our compatibility equations written out, and let's start with copper. Oh, that's ginormous. Okay, so if I'm looking at the copper, then I'm going to have a delta that comes from the internal force of the copper, the length of the copper, the area of the copper, the E of the copper, plus alpha delta T, L of the copper, plus force of the aluminum, length of the aluminum, let's see, area of the aluminum, E of the aluminum, plus alpha delta T, length aluminum, equals 0.01 inches. And now we can start filling things in. So I know that both of these are equal to the external F that's pushing back in. They're both in compression. So I'm going to have a negative force times the length of 12 divided by pi over 4, 1.25 squared. And I don't have any of the information here, so I'm going to have to go back to my chart. And when I go back to my chart, I'm going to find that we have 15 times 10 to the third KSI for our E value. So this is the delta due to that compressive force plus, okay, plus alpha delta T. So alpha was 9.4 times 10 to the negative 6. Delta T, our final is 400. Our initial is 60. And our length is 12. Plus, okay, once again, we have that negative internal force. We have a length of 6 inches. We have pi over 4. It is also 1.25 inches squared. Its modulus of aluminum is, I believe that's 10 times 10 to the third KSI, okay, plus alpha. So we have 13 times 10 to the negative 6. Delta T, 400 minus 360 is going to be 340, a length of 6. And this equals that gap, 0.01 inches. So we have everything in inches, inches squared, KSI. This is in Fahrenheit, which gives us our units, and this is in Fahrenheit. This gives us our units of inches, which is deformation. We have inches, inches, KSI, inches equals an inch. So now we just have to start simplifying. So I'm going to combine these two right now. So I have 12. Pi is a number, 4 divided by 1.25 times 1.25 times 15 e to the third times divided by, and then I have 6, enter. Pi is a number, 4 divided by 1.25 times 1.25 times 10 e to the third times divided by, and I'm going to add those two up. And when I do that, I get negative 1.1408 times 10 to the negative third F. Okay, now I'm going to do my temperatures and then I'm going to add them over to the other side. So I have 9.4 e to the negative 6, 340 times 12 times, and then I have 13 e to the negative 6, 340 times 6 times. Add those up, take them to the other side so that they're negative, add it to 0.01, and I get equals negative 0.054872. So let's go back and deal with this. That's actually negative. Let's find the reciprocal. Okay, the reciprocal. We're going to multiply both sides by the reciprocal. And when I do that, I'm going to find that the internal force is 48, not 4 point, 48 point, let's just call that 1. And our units were kips. So that's our internal force. So now I have to check, does it yield? Does it yield? And which is great because it said to calculate the normal stress anyways. So let's find that stress in the copper is the force in the copper. The length of the copper is 48.1 kips. divided by, not the length, divided by the area. So I have pi over 4, 1.25 inches squared. Pi is number, 4 divided by 1.25 times, 1.25 times, and divided by. And I get that the stress in the copper is 39.19 KSI. And if I go back and check, the yield stress for copper is 50 KSI. Okay, and then we can check the stress of the aluminum equals the force in the aluminum divided by the area of the aluminum, and I have 48.1 kips. Pi over 4, 1.25 inches squared equals, swap that out. Pi is a number, 4 divided by 1.25 times, 1.25 times, and divided by. And I get the same thing because it's the same amount of force and area. But again, remember, they're going to have different strains because they both are going to come from that stress strain curve. And they may have the same, well, in this case, they have the same stress, okay? They have the same stress, which is going to give us a different strain when we start looking at the material properties and the lengths and that kind of business. So this is less than, let me go back, I got sidetracked. This should be, the aluminum is 40 KSI. So they neither one yield, they're both safe. So we can call both the normal stress of the copper equals the normal stress of the aluminum equals 39.19 KSI. And now we want to find that change in length. Calculate the new length of the aluminum. So we need to go back to this part of the equation, and I know that the change in length of the aluminum is going to be, okay, it's going to be from the compressive force and the change in temperature, that thermal load. So if we go back, we're just going to plug it in up here. And when we do that, we have the force is 48.1, so 48.1 change signs, times 6. Pi is a number, 4 divided by 1.25 times, 1.25 times, 10 e to the third times. Let's try that again. 48.1, 6 times. Pi is a number, 4 divided by 1.25 times, 1.25 times, 10 e, dang it, e to the third times and divided by, if I did that right. So I get negative 0.0235 inches plus 13 e to the negative 6, 340 times, 6 times, 0.02652 inches. So our total length of change in aluminum is, whew, that is a tiny number, 0.003 inches. It is positive, so that means it is elongating. And it says the new length, so the new length of the aluminum has to be the original length, 6 inches, plus the change in length. So I have 6.003 inches. That would be my new length. You have to read the problems carefully to figure out what it is that they are asking you. So this time it asks us for the new length. So I found my change in length, and then I added that to my original length of 6 inches to get 6.003 inches. And there you have it.